Hello, welcome to a new live stream. Today the plan is to do some more C++ refactoring and more C++ and more refactoring. So we started this, I don't know, a few days ago with in the previous live stream. We kind of started working in C++. We started to create like a separate C++ library that we can include in both our bootloader and our kernel. And today we're going to continue working on that. So let's get started. So where we left things off was we kind of created this library here, which we called core. And we kind of started to create a couple of classes. For example, the device classes, the VGA text device, which is used to print text to a VGA device, like to the B8000 port, to the B8000 memory address. And we also created these devices, and we kind of started working on this file system stuff. Okay, so right now let's start working on another thing. Let's see. Okay, let's actually start by renaming this. And I'm gonna call this stage 2 old. And I'm gonna create a new folder. Name stage 2. I'm gonna leave the linker and the scan script as they were before. Also these CRTI, CRTN, I'm gonna leave them as well. The entry point as well, which looks pretty good. And what else we have here? Okay, so the x86.asm, there's a lot of assembly code here, and it might be a good idea to split it up, to break it up into separate functions, into separate files for all these functions that we have here. There are a lot of them. And let's start by writing main.cpp. And I'm going to also open the old main.c. And let's see what we want to do here. We have to basically add these memory definitions back as well. Hello. So these are basically like our manual memory allocation, memory management. In this file, we're basically just saying that, okay, I want to allocate some memory to the fast driver, starting from this address and having this size. And that's kind of how this file works. Okay, I'm gonna leave it as it is because we haven't actually worked on the memory manager yet, so it's best to just leave it. All right. Okay, and let's see what is the first thing that we have here is this clear screen. Okay, so now let's see how we can do that in this new bootloader. Okay, so first I'm going to add this declaration for the start function because we still need it. And if I remember correctly, last time we created, yes, inside this defs.hpp, we have these macros export and asm calls, so we don't have to type them manually every time. So we're just going to do export and then asm call, which means that this function is meant to be called from assembly. That's the point of this. Okay, and I'm going to start by including core defs.hpp. And now we have these definitions and stdint for these uint16s. All right. Okay, so greetings. Let's see. Okay, since we are making all the functions start with a capital letter, let's do this here as well. And we will also have to update our linker script. Entry point will be entry, yes, but in the entry code in entry.asm, we want to go to start with a capital letter. And here as well. Okay, so the first thing we did was to clear the screen. Let's see how we can do that. We have created this core arch VGA text device, and we are going to initialize a VGA text device here. And this is in the Arch i686 namespace, so and then we're just gonna call clear, and now we have cleared the screen. And let's actually make a little test to make sure this is still working. So I'm gonna write we have the, which was the one with the format. Okay, so yeah, I remember now. So we need to create this VGA text device, and I'm gonna make this a global variable. I think that might be. Okay, I'm gonna call it VGA device, and we're gonna clear it. But in order to print text to the screen, we're not using this text device because this one is just a dumb device that doesn't know how to do a lot of things. But we're gonna use this text device class here. So include core dev text device, and let's just create a text device. And let's call this screen. And in the constructor, we are going to pass this VGA text device. And now screen dot format, and let's see, hello world. And then let's just add an infinite loop so that we don't get a crash or something like that. Okay, let's try to build. Okay, so we do need to add core. So yeah, we do need to add this this libs directory to the include path over here. Now I've done this before, so I know that I had some trouble with scones when doing this. Basically, if I try to just, okay, this one doesn't exist. I mentioned this the last time as well. cpath doesn't exist. Doesn't exist that variable, so there's no point in defining it. cpp path is used for both C++ and C by scones. Now, if I would do this, just trying to add it like a relative path, this will not work. And the way I figured that out was through a lot of trial and error. And basically another thing that helped me, and if you ever have issues with scones, this might help you too, was to comment all of these com strings. By commenting all these com strings, you get the full command line for each of the command, and then you can actually see what is going wrong and what the problem is. And the solution I found that would work the easiest, that worked best, was to basically create a variable here in this target environment, or in the host environment. It's fine here as well. Okay, so we are going to append to this host environment. We're gonna append a variable, and let's just call this, I don't know, project there or something like that, or root there. Okay, root, and this will be host environment dot dir of the current directory dot source node. In sconce, basically, when you have there are two. Okay, so if you don't include the source node, it's gonna try to put, this will have the value of the build directory, and if you do put the source node, then it's gonna be in the source code, and that's kind of what we want here. All right, so all we have to do now is just use this root dir, which will be in our environment. So since this is a clone, then this should be fine. So we're just gonna call environment of root dir dot directory, and then we can this is gonna be this root directory where our project is, and here we want to go into source and then libs. I'm not sure if I even need this source node. Let's see. Let's give this a try and see. Okay. Okay, that seems to work. The only problem we have is some of these include paths. Let's also add core. So when we did it last time, we did not add core slash here. So that's what it's complaining about. Okay. Okay, so we probably need to do the same thing here into this sconce script. So okay, there's a few more. Okay, so now we've made some progress. All right. And it looks like something is not implemented. Yes, and one of them is cxa at exit. And if we go here to OS Dev, C++, this was one of the things that they mentioned here. So basically, we just need to add this to our code. And I don't think we even need to define anything inside it. Let's see. Okay, so apparently this cxa at exit is used to register a destructor that would be called when a shared library needs to be unloaded. In our case, this is not gonna happen, so we don't have to actually implement anything in here. We just need to have this function somewhere in our code. So let's just add it here to C++ and to this CPP folder, and I'm just gonna call the cpp support.cpp, and I'm going to define this function, and that's basically it. And okay, so we also need to do using the export. So include devs.hpp, and we're gonna export this. So basically export will make it so that it has the C style linkage, the C style naming instead of the C++ style naming. Basically, as you can see here, this is a C++ function name. And in C++, you know that you can you can overload functions. You can have multiple functions with the same name but different arguments. And this is how C++ implements that behind the scenes. It actually changes the name and adds some type information to the function name. In order to get the C-style function names, we just need to use extern C. And that should fix that issue. Okay, no return. Okay, let's just return 0 or something like that. But that should fix this issue. Okay, and now we have a few more issues. What is this? One way to figure out what the actual name of the function is to just do echo and paste the name that it gave us. And then we have a tool named C++ filter. Okay, and this would be the delete operator. So it looks like we are lacking the destructor, more exactly the delete operator. And which is referenced in character device.hpp. Let's see. Okay, this is a pure so this would be an abstract function, and it looks like it's also asking for it in VG text device. I wonder why it's calling delete. That's a bit odd, I think. But anyway, yeah, so we do need to implement a delete. I can stop the music if you want. Seriously. Do you want me to stop the music? I don't have a problem with that. 2 bits in. Yeah, okay, I'm gonna stop the music. No problem with that. Okay. You're welcome. No problem. Okay, let's see. So what I'm curious about is why it is asking for this delete. If I'm looking here, you can see that this delete has 2 arguments. It has a pointer and it also has a size. And I wonder if there's any information about that here. I don't really see anything here. But sure, I mean, no problem. We can implement a delete function that has this signature. And for now, we're not going to do anything. Okay, we're just going to do a to-do after implementing memory manager. To delete overloaded abstract classes. Yeah, that's a good question. Because what I'm lacking here is I'm lacking what am I lacking? Why is it giving me an error? A type. Okay, the type probably doesn't matter, so. Okay, let's see if... Okay, so that fixes the issue. A panic. I have no idea if I should or not. Maybe. Yeah, that's not a bad idea. Okay, but, Okay, so here in io.hpp, let's also create a panic function. So export void panic, which will just hold everything. So disable interrupt and hold, which will just stop everything. Okay. And let's just add this here. So include core arch i686 IO. And we're just going to do a panic. Okay, let's see if this works. And yes, we have hello world. Yay! We made some progress here. All right, now let's see how to move each and every one of these. Okay. I'm gonna close everything because I have way too many things opened. All right, so the first thing we did here was to do the disk initialize stuff. Okay. So let's also create these abstractions here in our stage 2. So previously the disk.c, if I go to disk.c, okay, so what this does is it basically wraps all the BIOS calls to the disk functions. So we're gonna create the same. So let's create arch i686 and let's just call this BIOS disk. I think that's a good name. Should not be a folder. And then a BIOS disk.cpp. All right, and this BIOS disk will inherit from, I think, the best, from log device is probably the best option. So include, okay, my head is probably in the way. CP, core arch, actually no, it's in dev. Block device. And let's create BIOS disk, which inherits from block device. And what am I missing? Nothing. Okay, so this should be okay. And here are the functions that we need to implement, and also these ones. So we have read, we have write, we have seek, and size. Okay, now let's see what we also had in the old disk functions, and because there's some functionality there. Disk.h. Okay, so we had this structure which contains the information about the disk. We can just include that over here because this is our instance, basically. All right, and I think this might also be a great time to also add support for the extended function, because we don't have support for that. We've added it to stage 1, but we don't have it in stage 2. So what we need for that would be just a boolean that tells if have extensions. And if we have the extensions, then we are going to call another set of functions. All right. For initialize, we just need the drive number, and we can just put that in the constructor. So BIOS disk, and it's going to receive the device ID. I think, okay, just ID is fine. And then read sectors. Okay, so previously this disk function here, it didn't read like, it actually just read a sector from the disk. It didn't read a specific block of data, but we're gonna make it read a block of data because that's more convenient with okay. And now let's do the implementation. Okay, let's start with the constructor. So this will be very simple. All we have to do is just initialize the ID. And yes, it might also be a good idea to read from, because in this disk initialized, we called the get drive parameters. So it might also be a good idea to do that here. Okay, this is something we are also going to have to do, is to create these functions. And let me think about it. Okay, I'm just going to create them here as static functions, since they are only required here. They're not called anywhere else, so I think it might be a good idea to just add them here in this file, biosdisk.cpp. And let's create. All right, so let's see in x86.h, and I'm gonna get all these disk functions. And let's just define them over here. And instead of this attribute cdecl, we're just going to use asm call. everywhere. And we also need to export these. Okay. All right. And now that we are here, let's also do the other functions, which would be the extended ones. And for the extended functions, we basically need, I think there are two. Let me just check. So int 13h. Yes, we need to call this check extensions present, and then we have the extended read. So two functions for that. And then extended read, which just needs the LBA. So you int 32 LBA, then account, and then where to place the data, which looks pretty good. Let's see. Okay, so the number of sectors to read is 2 bytes, but some biases are limited to 127, so let's just leave it 1 byte. And the rest looks pretty good. Okay, now, yeah, okay, so let's create a separate initialization function. And the reason why I'm doing this is because it's usually not a great idea to do a lot of things in the constructor. And we also want to check the result to see if it has succeeded or not. So let's create a separate void initialize, or actually bool. All right. And our first step would be to check if the extensions are present. So have extensions is equal to this extension is present. And if they are not present, then we will need to read the parameters like we did in the previous implementation. Disk.c. All right, and let's see. So these are uint16s. All right. So we can just pass these instead of having. Okay, so if get drive parameters of cylinders m underscore sectors, m underscore heads. Okay, so if this fails, we just return false. We don't need to copy anything anymore here. Don't need to set these because they're already set. So that's basically it. That's the whole initialization. Return true. Okay. Then for the read. Now this is where things get a little bit more complicated. Okay, so basically the minimum size that the BIOS can read is 1 sector. But here in this BIOS disk implementation, we're basically trying to read just this much data. And this size may be smaller than, it could be smaller than 1 sector, it could be the same size of a sector, or it could be bigger than a sector. And we have to basically keep track of that. A 64-bit bootloader, sorry, but no, that's a lot more complicated and a lot more work. Okay, so let's define sector size to 512. Okay, I'm pretty sure there's a C++ way of defining this, but for the moment, let's just leave it like this. And what I'm gonna do is I'm gonna create a buffer here. So uint 8 of 1 sector. And the way this is gonna work is we are going to read 1 sector into this buffer, and then we are gonna copy the data over here. And then we're gonna read the next sector and so on. And we also need a way to keep track of the position. So let's add the position as well. And the size. Yes, thank you, 2 bits. That looks pretty correct. Static inline. But does that work? Okay, static inline const expression int. Okay, that's a lot of qualifiers. All right. So now we also need to initialize the position and the size. These are definitely things we want to initialize. Position will be initially 0, and the size we're also setting it to 0. And inside initialize, we need to figure out how big the disk is. That might be a good idea. Can we do that? Good question. That's a good idea. That's a good question. Let's see. So this read drive parameters is probably the way to do it without extensions. We just multiply the number of heads with the number of cylinders with the number of tracks, and then we get the size of the disk. That's probably the way to do it. Inside the... So if we do have extensions, let's see if there's a way to... Okay, so there's extended read drive parameters, so we probably need this. And this will give us the physical number of cylinders, heads, and sectors per track. These are useless, but it will also give us the number of sectors, the total number of sectors, like the LBA stuff. Okay, so let's also add extended read drive parameters then. Okay, that's a long function name. Okay, so we want the drive. I don't actually care about this at all. I'm just not gonna add it. And what does information flags mean? I don't see any description here. All right. Basically, what we care about is this number of sectors. And there's also these bytes per sector. I wonder if bytes per sector can be different for certain disks. Maybe there are disks which have 4 kilobyte sectors instead of 512 bytes. And this might be useful. Okay, let's do that. Okay, let's see if there's another source of wisdom here instead of Wikipedia. Okay, this one doesn't have the extended function, so not useful. Okay, so there's the Ralph Brown interrupt list. This is usually the best source of information for these BIOS interrupts. And we're looking for int 13. And the function would be 48. 48 gets drive parameters. Okay, so it looks like this buffer here, there are different versions, and there's a version 2 and there's the version 3, which will also have some additional information. So when we call this function, do we specify the size? No, we don't, which I find odd. We might need to fill this size at the beginning. The BIOS might actually check this number before filling the structure. I think that might be how it works. Okay, and then there's also whatever this means. And in version 3, okay, so there's some additional information here, but nothing that's really useful. The interface type like ATA, OTAPI, SCSI, and so on. Okay, this could be useful though. Because one of the biggest difficulties when switching to protected mode is that you get past this ID from the BIOS. You have this drive number. And there's no way to correlate that to what port the BIOS actually uses for that. There's no way to find what it means. And this information might help with that. But yeah, the biggest issue is probably the non-standard that many BIOSes will not support this at all. And I'm pretty sure that the Chemo BIOS just does the minimum and it's just gonna have the version 0. It's just gonna have this and nothing from here. I don't know for sure, but I'm just thinking out loud here. Okay, and the information flags. Okay, so whether the drive is removable, whether the cylinder head sectors per track information is valid. Okay, that's good to know if you need that. Drive can be locked. Yeah, so for example, a CD drive, you can lock it and then it's not going to eject. Even if the user presses the button, it's not going to eject. So that's what drive locking means. Okay, so there's some information there, but nothing that I think is super useful for what we're trying to do right now. And okay, so the first one is the size of the buffer, and it says here call in parentheses. So basically we have to pass that size here. We could try to pass it 42H and see if we get any extra information, but yeah. Okay. So for this function, instead of passing everything as a parameter, let's just define the structure in C++, and I'm gonna just pass the structure here. So struct extended drive parameters. And we're gonna pass a pointer to the structure here. All right, and let's just add the version 1.0 parameters. All right, so we need uint16t params. Okay, size or param size, or how should I call it? Param size, and then we have the information flags. And then for dwords, dword it is 32-bit. Cylinders, heads, and sectors. Then we have the total number of sectors, which is a 64-bit number. And then the bytes per sector, so uint 16 bytes per sector. Okay, let's see what else we can change here. I was also thinking about doing a similar thing to the extended read, because here we also need to pass a pointer to a structure which contains all the information about the read. Let's do that as well. Struct extended read parameters. And this structure basically has 4 things. The Ralph Brown might be nicer to copy. So extended read. Okay, there's an optional parameter here for version 3 of this thing, but we're not going to add that. Okay. Param size, and then the next byte is reserved. Then the number of blocks to transfer, so uint 16 count. transfer buffer. Yeah, this is gonna be a bit of an issue for us because this is gonna be in the segment and offset format. Transfer buffer, and we're gonna have to convert it. And then uint 64 LBA. So I don't know, buffer I think is just fine. And then instead of passing all of these, we're just gonna pass it like this. Okay, this looks pretty good. Okay, now when we get the drive parameters, so we will also have to add this for the extensions. So we'll define extended drive parameters, and then we're just gonna call all right. And yeah, something to do here is to convert this from whatever this is to a segment and offset. So I think this is only relevant here in stage 2. So let's add it here. Memory real memory.hpp. And let's do a define. Actually, let's just do a template. Why not? Let's just do a template. So a template, type name T, so we don't care what type we are calling this function with. And we're just gonna return a uint32. And we need stdint for that. So the point here is to convert this from whatever type it's here. So it might be a void pointer, it might be an int pointer. So regardless of what type this is, we're just gonna convert it to a uint32. And I think reinterpret cost is best here. Reinterpret cost to uint32. And to convert this to segment and offset, we basically... So we are going to take the... Okay, so there are many ways in which we can implement this. And the way I usually prefer to do this is kind of like this. So let's say that I have the address 1, 2, 3, 4, 5. The way I prefer to do this is to just take 1, 2, 3, 4, 5, 1, 2, 3, 4, and use this as the segment, and whatever is left, use that as the offset. The reason why I prefer to do this is because most of the time If you don't do this, so if you just split it like this and have this as the segment and this as the offset, then you might get some issues with overflowing. So if this goes to FFFFF, then it's gonna overflow and it's gonna go back to 0. And you're gonna be in segment 1 and offset 0. And yeah, it gives you the best range. That's the greatest, that's the best explanation, yes. Okay, so address int shifted to the right by 4 bits. And okay, and this would be, okay, so let's just do uint32. This is the segment. Offset is address and 0x and just 0f because that's everything that's left. And this is okay, and now we are going to return segment shifted to the left by 16 and then adding the offset. So since this is little endian, what this will translate to is the offset will be in the lower bits and the segment will be in the upper bits. Okay. Okay, and let's include real memory.hpp. This is fine, so we can do the conversion. Yeah, we can do the conversion either in assembly or in C++. Until now, I've done it in assembly. It's not that pretty, but it works. So I'm just gonna leave it there. The only place where we will need to do the conversion is this buffer over here. And I'm thinking of just not doing this at all here. Just passing this structure to the assembly code and do the conversion in assembly. But it's always more convenient to do it in C++. It's always easier. Okay, fine. We're gonna move all the conversions to C++. If but yeah, I'm not gonna change all this code. It's just too much to change. We're gonna do this conversion in C++ and the parameters, I'm just gonna leave them in assembly, I guess. Okay, now let's create BIOS disk. Okay, we can't have the same name, so let's just use disk.asm. And until now, we had everything here in this x86.asm, but let's not do this anymore. I'm going to place these two macros for entering and exiting protected mode, and also this linear to segment and offset. Okay, let's have separate files for those. So protected mode.inc will contain these macros. And we should also have a guard. So if not defined, and if. Okay, and let's just have another one for the linear to segment offset macro. Okay, I'm just gonna put it here as well. Whatever. Maybe not the best place, but it's fine. If I manage to get symbolic debugging working, yes, it actually, I was able to debug from the kernel when I did the ELF video. It doesn't work for stage 2. It works for the kernel, but not for stage 2. And the reason is because stage 2 is still not in the ELF format. Stage 2 doesn't have symbols right now. And to get symbols, I would have to modify stage 1 and add symbols there. And make, add an ELF loader written in assembly there. And, that has its own difficulties. One of them is that we are already using most of the space here. If we go into the stage1.map, you will see that we are using most of the space here. We are... Okay, so the BIOS footer begins at FE, and the read-only data is the last section. I don't know if these add up, but in any case, we have very little space left. And if I remember correctly, we had to delete some code for it to fit, so, or to delete some strings and that kind of stuff. Yeah. Okay, so let's include. I hope this works because NASM is not very happy about. Okay, let's see. Protected mode.inc. The limit of what exactly? The limit of stage 2. I still don't understand the question. How big stage 2 can be? Is that what you mean? Yeah, so... No, I did not have to delete stuff from stage 2. I had to delete stuff from stage 1. For example, to fit the FAT32 file system headers, which have a lot of junk. Like 12 wasted bytes here, just reserved. Yeah, yeah, I had to delete, for example, some of these constants at some point. I had like a loading constant here, a loading string that I deleted completely, just so that it fits. So yeah, getting stage 1 to fit in 512 bytes is difficult. There's also a limit for how big stage 2 can be though. So right now the stage 1 loader will work probably up to 64 kilobytes, I think. I'm not sure if it can handle changing the segment. I'm not sure if I implemented that in this loader. If I'm taking care of the segment, I don't know. I have to check. But also there's another issue, which is actually not great. So did we relocate this code? No, we're not relocating. Yeah, so another issue here is that I'm loading the stage 2 at address 500. So stage 2 goes at 500, and then at 7C00 there's stage 1. So yeah, that's not great. At some point I'll have to change that. The best solution would probably be to move stage 1 to relocate itself to 500, which would leave me with the most available space for stage 2. But yeah, I'm gonna have to do that at some point, probably. If it stops, if the stage 1 stops working, then that's probably why. Okay, so we are implementing these disk methods. Let's see where we are at right now. Okay, so we have the get drive parameters, which is from the old code. We also have reset, which is working, and we have read. And we have to add the extensions present, extended read, and extended get drive parameters. Okay. Into PXE? No, I haven't looked into PXE yet. Sorry. Okay. Okay, so extended get drive parameters. And we can just copy most of the code from the other functions because it's mostly the same. So yeah, we create the call frame, we enter real mode, we will save the modified registers, and then we need to set up the BIOS call. Let's see what arguments we have. So we are starting with, is it this one? I think so. Yeah, it's 41. Yep, this is the one. Okay, so AH needs to contain 41 hexadecimal, BX has to contain 55AA, and DL has to contain the drive number. So that should be pretty easy. Okay, DL is set up here. Then 55AA hexadecimal in BX. And the function number, which is 41 in AL or AX? AH, yes. All right, and then we call int 13, and then let's see the return. So carry flag is set on error, which means that the extensions are not supported. So yeah, I'm basically setting the carry flag here at the beginning. If and this will clear the carry flag if it succeeds. But if it fails, what I'm doing here is I'm putting 1 in EAX and I'm subtracting with borrow. So if the carry flag is 1, then this subtracting 0 means that it will actually subtract 0 plus the borrow, which is 1. So EAX will be 1 if true, so and 0 if false. Okay, the modified registers are so in the cdecl calling convention, we don't AX is used to return, and we do only need to save BX. DX is saved by the callee, so the caller. Okay, so push BX and that's it. Okay. And we should also test that BX is AA55, so it should flip those. That's also a good idea. Okay, so let me think. What we can do here instead of this, because I want to have a fail state. Okay, so if carry is set, then we are gonna jump to error. And let's have error be to set EAX to 0. So move EAX to 0. And if there is no error, then we are also going to compare BX to AA55. And if it's not equal, we are also going to jump to error. Okay. And if there is no error, then we are going to put 1 in EAX. So move EAX1 and jump to NDiff. Okay. Restoring the registers, just BX. And then there's this code which enters protected mode. Yay, welcome Nebula Developments. Great to have you here. Okay. I did a bit of a mistake here because I was actually implementing if the extensions are present instead of... Okay, so this is supposed to be extensions present. Okay, and now let's do the next one, which would be extended read. Okay, for extended read, let's see what parameters we need. Okay, so the only thing that we need is the SSI should be set to the address of whatever we passed as a parameter. That should be easy enough. And other than that, the drive number in DL and 42 hexadecimal in AH. So 42 hexadecimal in AH, the drive number in BL, and then the read parameters, linear to seg offset, pp plus 12. That's basically where the second argument is. And we want to store this in ds and si. No, I never heard about Cosmos OS dev kit. So what is it? Is it like an operating system? Oh, to make an operating system in C#. Nice. That is cool. The only operating system in C# that I've ever heard about was that one from Microsoft. It was called Singularity. That's the one. That's the one I've heard about. But yeah, very cool. Making operating systems in C# is not that easy actually. The biggest hurdle there is the runtime. You basically need to implement a lot of things for it to work. And I'm not even sure if it's a good idea. Because in an operating system, you want to have control over a lot of things like, you know, memory and where things get stored in memory. And C# is kind of like the opposite of that. It doesn't let you control where things are stored in memory. So I don't know what to say, how good it would be for the build time. 5 minutes on a good PC. 5 minutes is nothing. The project I have at work, at my workplace, takes like 40 to 50 minutes to build. On a pretty good laptop, I'd say. A pretty beefy laptop. So 5 minutes is nothing. Okay. Alright, so for the extended read, let's finish this one. This should not take that long. So this linear to segment offset, it takes the address that we want to convert to segment and offset, then the segment, the register where we want to store the segment. This is the register where we want to store the offset, and this is just the 32-bit version of this register, because we kind of need it to get the lower bits. Half a day to build from scratch. Wow, yeah, that's a lot. Yeah, there are big projects out there that take a lot of time to build. Yeah. I also used to work at the place where they had a project where if you had to wait for the build, yeah, it would take about the same, about a day or even more. So the best solution we found to do that is to have a tool called Incredibuild. And Incredibuild basically takes all your build files and it creates like a distributed network, and you're basically using the computer of all the developers in your team and building on all of them at once. And with Incredibuild, the build time would be about a few hours maybe. So yeah. Yeah, Chrome is a pretty big project. Indeed. Okay. So let's see. Carry flag is cleared if successful. And AH will contain an error code. Okay. And the block count inside this structure is going to modify to the number of blocks successfully transmitted. Okay, that sounds pretty good. So we can just use that subtract with borrow trick here as well, instead of the more complicated. Okay, any modified registers? Yes, we have DS and ESI, so let's save those. DS and ESI, and we have to pop them after pop DS and pop ESI, but ESI should be first because we should pop them in the reverse order, and then the rest, which looks pretty good. Okay, extended read is done, and what we have next is extended get drive parameters, which is probably almost the same. Let's see. Extended get drive parameters is function 48. So that's the first thing that we need to change. 48. Drive number in DL, same as before, and the address in DSSI, and we already have that. So it's done. That's it. That's basically it. And here's the structure, and we've already looked at that. Okay, nice. Basically, we are done implementing these. Okay, So let's see what's left to do here. In the initialize function, we've read the drive parameters, but we haven't saved anything. And what we do want to save is the size, so m size. Okay, let's also... I haven't implemented assert yet, but it might be a very good idea to do that, because I want to assert something here. Okay, I'm just gonna add it here in assert.hpp. Okay, so this will just call a function called assert underscore with the condition. Okay, let's do it this way. So condition, and then we call this assert, or is better. Okay, so what I'm doing here is, so if condition is false, then okay, so if condition is true, then this will short circuit. That's what it's basically called. It will short circuit and this will not get executed. But if the condition is false, then this operator will not short circuit, and this assert will be evaluated. It will be called basically. And all we care about here is just the string representation of that condition, and then the file and line, and maybe the function, but func I think is the right name, if I remember correctly. Okay, and then the implementation. And yeah, it's sad that Visual Studio doesn't exist for Linux. There are some alternatives, but nothing is as good as Visual Studio. I agree. I really don't like using Visual Studio Code. I mean, it's the best editor on Linux, but I don't really like it that much. It has a lot of issues with the autocomplete. It doesn't work super well, but at least it's flexible. It has a debugger. It has support for creating build tasks, all kinds of build tasks. So yeah, it's the best we've got, I suppose. Okay. And now the implementation of assert. And here we have a bit of an issue because we don't have any... We don't have the debug stuff. Okay, and I think this might be a good idea. Okay, so what we want to do here is to print a message, and we're gonna do that in just a moment, and then I'm gonna call the panic function. Okay. Okay, for printing messages, it might be a good idea to implement that debug stuff that I had in the kernel. Okay, so debug.hpp and debug.cpp. All right. Should I create a static class or a namespace? I know that static classes in C++ aren't really a thing. It's just a class that doesn't have all the functions are static. So that's why I'm thinking of creating just a namespace for it. Either is fine, I guess. Okay, and let's take the debug stuff from the kernel. So I have all of these functions here. Okay, so instead of defines, I'm just gonna create functions here. So debug module const char format and then the variadic arguments. And let's also create one for info, warning, error, and critical. All right. Variadic templates. I don't like those. I don't like those. I'm not a fan of variadic templates. Sorry. Um, okay, so let's see. I will also create a function here to add um, okay, let's see. So we have these text devices. So okay, add output device min log level. So minimum log level, and then the device. Core dev text device. Okay, and this is how we are gonna initialize this debug module, basically. All right. And let's create a blank namespace where we will create a little array of these structures. And which will contain basically a log level and a text device. And yeah, it might also be a good idea to add a boolean for color output. So bool. Okay, the device will be the first. Okay, and a log level, a minimum log level, and then a color output, and whether to have color text or not. Okay, and these are gonna be the output devices, and let's have a maximum. Of, I don't know, 10 devices, I guess. It should never be as large as this, but it's always good to have a maximum here. Okay, and an integer output devices count. Now, if our static constructors are working, then this should be initialized to 0. All right, and inside this add output device, what we have to do is just output devices of output devices count dot device equals device log level is min log level and colored equals colored. Okay, and let's update this definition here. All right. Now, when we are writing some messages, for example here, let's create void log. We can make it static because it exists only in this function. And okay, we're gonna have the module, the log level, the format, and then the VA list. And then we are going to implement all this stuff we had in the kernel. Debug.c. Including these beautiful colors. I also need this enumeration. And yeah, I'm going to put this in the header. Now, I cannot make this an enum class. Actually, I can. Okay, so let's just make this enum class level and debug info warn error and critical. Okay. And what seems to be the problem? I think it's an issue with Visual Studio Code. but must be a class or namespace name, but it is. Oh, okay, so it's in the debug namespace. And it's still not happy. Okay, whatever. Okay, so these are the log severity colors. Then we have the reset color. Then we have the output devices and the output device count. Okay. And now let's implement this log function. And I'm just gonna copy all of this. And we're gonna basically iterate through all the output devices. So for int e equals 0, I smaller than the output device count, I plus plus. If the level is if the log level is smaller than the g output devices of I dot log level, then we will continue. It's really annoying. This is really annoying because VS Code doesn't like this syntax. Okay. Debug level is not a type name, but what is it? It's an enum class. Oh, yeah, sorry. This is how you correctly define an enum class. Okay, so now the errors are gone. And yeah, instead of fput s, now we have the output device. So output devices of I dot device, and we're just gonna call write the color. But only if the device is colored. I think C++ supports the syntax as well. It's just VS Code is not very happy about it. Yeah, okay. I'm just gonna leave it commented for now until I finish writing this file. Okay. Okay, so we have to cost this to an int, static cost of int. This is the annoying thing about enum classes, because if I want to use them here, I just need to use static cost. All right, then we're gonna print the module. Okay, then we are going to call the vformat function. So there's vformat using the user given format string and arguments. Then we need to call the color reset. Reset color. And then we will print the end of line. Okay, so this looks pretty good. And all that's left to do is just call this from all the other functions. Level debug format and then args and va end of args. Okay, and now let's uncomment this and see if what does the compiler have to say. Yeah, so the only thing it's not happy about is that this is not an integer. So yeah, we have to either cast it or just use static cast to int of this. Which looks even uglier. I would honestly just not use enum class for this, but fine, I'll just leave it. Okay. We have some issues, but they are not in this file, which is great. Goodbye. Yeah, and now, because I kind of started just with the assert, now we can just call include debug.hpp, and we will do critical assertion failed. And then we will print in file line function. Okay. And now we have assert, which is great. So let's go back here. And I want to assert that we need to include core assert.hpp. So we want to assert that the number, which one was it? Bytes per sector is the same as the sector size that we are expecting it to be. Okay, func is undefined. I think it's function. Is that correct? Hopefully. I think that looks good. Assert.cpp. Okay, it's called file name, not file. Sorry. All right. Okay, we're getting some errors here, but I think we are fine for the moment. From void to bool. Okay, so let's just make this assert boolean, I guess. And return false. It's not going to return anyway, but that doesn't matter. Just to avoid that error. Okay, no return statement in BIOS discrete. Okay, we haven't implemented that one yet. Okay, we're done. That's it. Okay. Yeah, and let's set the size. That's what I wanted to do here. Size equals sector size multiplied by the parameters dot sectors. Okay. The implementation for size will be very simple. We are just gonna return underscore size. This is a uint32. Let's make it uint64. And the position as well, I guess. Because in these extended functions, we can have up to 64-bit sectors and stuff, so might be a good idea. Okay, read and write. So I'm gonna copy the old read from disk.c. Oh, we also need this LBA to CHS. Okay. Yeah, this read implementation is gonna be a bit different. Okay, so let's create some private functions. One for virtual pool read next sector. Instead of reading like an arbitrary number of sectors, we are just gonna read the next sector based on the current position. Okay, and inside read, while size is greater than 0. Okay, so let's think about how to implement this. So we have some data in this buffer. Yeah, if this is the first time that we are reading from this disk, then we probably don't have any data in this buffer, but if we've already read, then there's some data in this buffer. And the position should indicate... okay, so it might be a good idea to initialize this position to something like -1, just for us to know that there's no data there. So we are going to initialize it with -1. -1 converted to a uint64 is just going to be like ffff many times. Okay. So the first thing we need to do, if position is -1, then we need to read next sector. Then, while size is greater than 0, the maximum we can read is the minimum between the size and the size of a sector, so sector size. Actually, no, it's not even sector size. It's however much we are left from that sector size. Okay, so position will always... Okay, we can know how much... okay, so here we need to set the position to 0. Okay, so if I divide position by... If I get the remainder of position divided by the sector size, that should give me how much bytes I've already read from the current sector, from the sector that's in this buffer here. I don't know why I chose to code in the C# style. It just kind of did, without thinking too much about it. So, what the amount of data we can read is pos divided by the sector size. But this is also a bit tricky, because if pos is divided by sector size is 0, then... Okay, so this gives us how many bytes we've read. To get how many bytes there are left, then we need to subtract the sector size from this number. So, size, the amount of data that we can read in this iteration is the minimum between however much data is left, and then sector size minus this number, which gives us how much data is left in the buffer. So let's just make this more clear. Left in buffer is this. And then we are going to perform a mem copy to data from the buffer plus okay, so we also need buffer position, which is this. And then left in buffer is just sector size minus buffer position. So okay, buffer plus buffer position, that will be the source. Data is the destination where we want to write. And then can read is how much we can read there. Okay, now we are gonna subtract everything. So size minus equals can read. Then we need to add to the data pointer can read. And I think, yes, also the position. So pos plus equals can read. And if the size is still greater than 0, then we will read the next sector. And this while loop will loop until size becomes 0. And yeah, we haven't calculated how much data we've read. So let's do that as well. We can do that by just using this position here. So return the position minus the initial position. And then we can return how much data we've read. And I think this looks pretty good. We still have to implement min and mem copy, and read the next sector, and we will do that. Okay, for the write, we're not gonna support it here at all. So we're just gonna return 0. Now, seeking. This is gonna be a bit of a challenge. How to seek. Actually, no, it's not that difficult. So let's do seek. Okay, so if we are seeking, if the seek position is from the beginning, then what we have to do is just reset everything. So we are going to initialize mpost to -1. And I think that's everything I need to do. Yep. And whenever we are going to try to read, then it will read the first sector. So that's it. Then if we are trying to seek from the current position, then we need to increment position by that relative offset. And then we need to update what the sector that we have here. Read next sector. Yeah, I think this should work. We're gonna implement read next sector so that it also works even if this position is not aligned properly. Break, and if we are seeking from the end, then we are gonna set the position to the size. And that's it. Okay, now inside read, I've also realized that we also have to keep track of whether position is smaller than size. So over here, yeah, I think we can just use read next sector to verify. And we just need to check here. So we can use read next sector to verify if we have reached the end of the file. And then all we need to do is just verify that the position is not greater or equal to the size. Then we just return 0 in this case, because there's nothing to read. We've reached the end of the file. All right. And I think all that's left to do is just implement read next sector. And previously I had this read sectors function. But it's going to be a bit simpler now. All right, and let's implement read next sector. All right. So what we need to do here is first to get the LBA of what sector we want to read. So you need 64T LBA equals m pos divided by the sector size, and that's the sector that we want to read. And then the next step depends on whether we have extensions. If we have extensions, then we will have to create one of these extended read parameters. And param size is size of extended drive parameters. Count is going to be 1. And LBA reserved should be 0, of course. What else do we need to set? The count and the buffer, and then the LBA. To segment offset of buffer, and then the LBA is LBA. And we will just return i686 extended read of MID and these parameters. Else, this is where things are a little bit more complicated, because we need to make a conversion using disk LBA to CHS. and I will implement this function in just a moment. Oh, yeah, I haven't done this. To reset the disk and retry if it fails, and it might be a good idea to do that. And okay, and we're just gonna return okay. Yeah, we can just leave this here and have a single return point. Okay, and then same thing for this one. Oh, and yeah, if this fails, then we need to reset. So if not okay, then we will call disk reset. Okay, same thing here. And we will do a not extended read, just a normal read using these parameters here. Okay, now we need to implement LBA to CHS. This doesn't have to be virtual. Why did I make it virtual? Okay, and for the implementation, let's just put it here. And I'm gonna copy the implementation from here. Okay, this looks pretty good. What is left to do is main and mem copy, so let's take care of those. Back to core. Where does C++ put min and max? Okay, so these are templates inside algorithm. Okay, and I'm just gonna define a template for min and max. Okay. This looks much better. And let's just keep the naming consistent. And I'm also going to create memory.hpp. And let's create copy. Now for something we have to do here is, even though we have these copy function, for example, memory copy, we still need to implement memcopy because the compiler expects us to. So that's kind of unfortunate. And we are also gonna export it, and for the moment we'll just leave the implementation here, but eventually we will move it we will move this implementation to assembly, because doing memcopy this way is very slow. Actually, let's do this right now. Let's implement this memory copy in assembly because it will be much faster. So include core devs.hpp. And instead of implementing this twice, let's just use using copy equals memcopy. Okay, it's not allowing me to do this. I wanted to... Can you do function aliases in C++? Okay, so you can just do this. That looks very ugly. Okay, there we go. Const expression auto copy equals memcopy. There we go. And now we have an alias for the memcopy function, which is more C++ like. And now let's implement memory asm.asm. The compiler is not going to be happy if we have... actually, we don't have any CPP file here, so I think we can do this. And let's declare this as asm call. And now let's implement memory copy. Now, how would we implement this function? And the answer is first by setting up the call stack, just like we did to any other function. Setting up the call frame and then restoring the old call frame, and then we can use the repeat the repeat move SB to do this. And this will be a lot faster than just copying it by hand in C++. So the syntax of the way to use this is to set into DSSI the source, and then ESDI is the destination. So first, let's set the source. Okay, destination is the first argument. So let's start with EDI and EBP plus 8, because we have the call frame, which is 4 bytes, and then we also have the return address, which is another 4 bytes. So the first argument will be at EBP plus 8. So this would be the destination. The source is at EBP plus 12. And then we have the count in EBP plus 16. Okay. And then we will call rep move SB. And that will call move SB for ECX a number of times. And that's it. That's the memory copy function. And this will be a lot faster than just doing it manually. Okay, back to our disk function. Now we have to include core memory, HPP, and core CPP algorithm. Okay, and I think we are done with the disk functions, which is great. Let's see what happens if we try to build this. Okay. That's a lot of errors. Unable to include protected mode.inc. Oh yeah, okay. So I knew this was gonna happen. NASM is not as good as C++. The preprocessor of NASM is not as good, and even if you use quotes, it's not going to include files from the current directory. And we have here this flag which tells it to add the stage 2 directory as an include directory. So we'll just have to add the path manually to arch i686 and then protected mode.inc. And that should make the error go away. And we still have some things which undefined reference to get drive parameters. Oh, and I know what the problem is. I did not rename these functions. Okay. And that's it. It works. Great, 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 great. To use GCC's preprocessor in assembly. That's a spicy idea. But no, I'm not gonna do that. Okay, so now let's do something here that uses the disk, and let's try to initialize the disk. Okay, and let's initialize the BIOS disk. And if the initialize fails, we're just gonna print a message and panic. No default constructor exists. Oh yeah, I have forgot to pass in the boot drive. Okay, and if this fails, then yes, now we have debug.hpp, which is great in core debug. And it is also a very good idea once we initialize this text device, this screen device, to add it to debug, add output device, screen, the minimum log level. Let's just do debug level info and color output. Yes, please. We want colors. In fact, actually the VGA screen doesn't support colors, so let's just not do colors here. But let's also create another device because we have it. We also have the E5 text device. E5, E9, sorry, E9, what is it called? E9 device, just E9 device. Debug device. And we can also add this as an output device. Okay, text device debug, which uses this E9 device. And then I'll add output device debug, and we can have a different log level there. We can have debug and with colors. Assembly with CPP. Yeah, okay. Yeah, NASM isn't that great either, but at least you know what to expect. And the documentation is kind of so-so. I wouldn't say it's great. Okay, and if this fails, then we will just bail out to initialize disk. But if it succeeds, let's just call this okay. Okay, we still have some core dev character device. Okay, done. Phasm. I've never used Phasm. I've always used NASM. From the first time I started to learn how to make operating systems, I just used NASM and never tried to use anything else. Failed to initialize the disk. Yeah, that's great. All right. No idea why this is happening. So let's try to figure this out. Yeah, that sounds nice. I've never actually tried it, so I don't know. Okay, looks like something is failing to initialize, and let's try to figure out what exactly is happening. Okay, let's go into BIOS disk, initialize. Okay, so what could fail here? We're basically checking if the extensions are present, and if they are present, then we are trying to get the drive parameters using the extensions. Otherwise, we are just using the old get drive parameters. And something seems to be failing. So what better thing to do than just call debug? And let me open a terminal for this. It's easier to use a terminal. Scans debug. And we will need to create a breakpoint. Let's see, in stage2.map. Okay, this is a bit annoying because the function names are now mangled in by this C++ thing. But there's a very easy way to fix that, and that is to just run it through the filter. So cut build stage2.map C++ filter, and let's just use less. And there we go. Now we have the correct names for all the C++ functions. Okay, so the problem, okay, where we want to break is inside this initialize function and see what is happening here. So let's try to figure out where this function is. So let's search for BIOS disk initialized. It is at 8DE. So we will put a breakpoint at 8DE. And we will continue. Control XA. Okay, we are not seeing the assembler because I modified this script the last time. So let's try to see. Okay, layout ASM, that's the command. Layout ASM. Okay, there we go. So first we are setting up to call function f71, and if we go here, f71, that would be disk extensions present. So let's go there. Okay, something jumped unexpectedly, and I'm not sure where it's ended up, so let me just start again. Okay, layout assembly, and we want to break at, I forgot. BIOS disk initialize. Where are you? 8DE. Okay, and we are at 8DE. So let's put another breakpoint at this call here. So 8F3. I think that what I did wrong was I just called NI instead of SI, which kind of jumped more than one instruction, and I did not know where it ended up. Okay. And now it's calling this function, and does fin work? No, it doesn't. So let's just step through. What is happening here? I'm lost again. Yeah, this is the annoying thing about debugging assembly. Sometimes you get lost. Okay, 8DE. Okay, so let's just break at 8F8. After this function call, because this function call should work just fine. Okay, and now we have the result in EAX. So let's print info registers. EAX is 1, which means that yes, we do have extensions. So the next step would be to set up the function call for the get drive parameters with the extensions. Okay, and we haven't jumped, so now we are probably inside this here. Okay, let's see what happens when we call extended get drive parameters. Looking here, it is at address 103A, so let's break there. 103A. All right, and let's go step by step. Okay, so let's just go all the way to this int13 instruction, and then we will check all the arguments. So we'll break at 0x 1072. And then info args, info registers. Okay, AH is set to 4800, which looks correct. Then DL should contain the drive number, which in our case is 80. That looks pretty good. And DSSI should contain the buffer for the drive parameters. SI is 12 and DS is FD5. So the address would be FD5C, I think. Something like that. Which is probably fine. Yeah, it's fine. Okay. So let's put a breakpoint right after this int13 hexadecimal. I don't want to step through this interrupt with a debugger, so break at 1075. Okay, and the flags, I don't see them here. Okay, we don't have the carry flag, which means that this has succeeded. All right, so what's going on here? Hold on a second. Wait a second. Did I do something wrong? Did I forget to save EAX? No, but I've skipped a couple of instructions here. So EAX is 0. Yeah, I think I just skipped a couple of instructions, unfortunately. And I cannot go up. That's annoying. Yeah, I skipped it, so I think it gave me an error. And I think I know why. Something I missed is there might be some padding here that is added by. So let's just set this to packed and save for this structure. And I think that might be the reason why we got that error, because it got a param size that it did not expect, because yeah, we have these uint8s, so the compiler is definitely going to add some padding for that. And I think that's the problem. Let's try to run this again and see if changing this fixed it. Okay, it's still failing to initialize the disk. But did we set the size before calling this function? I think that's the problem. Oh yeah, we did not set a size. Param size is size of extended drive parameters. All right, scans run. And there we go. Fixed it. Yay. And now we have a successful disk initialization. Okay. That's great. We made quite a lot of progress. But there's more to be done. Okay, so we have created a disk. Now we need to do the partitioning stuff. So we need to see if the disk is partitioned, and if it is, we need to basically obtain the correct partition. Let's go to main.c. All right, and here I had this detect partition function, which did that. And I think this is something we can actually implement here in BIOS disk. Okay, so okay, let's just create an MBR detect, and then that doesn't belong to any architecture, so we can just create here under dev MBR. In fact, it might be a good idea to create this in the shared library, because we're going to want to have this in the kernel as well. Does this belong under device? Yeah, I think under device is the best place. So mbr disk.hpp. Not a folder. mbr disk.hpp. mbr disk, and this will just wrap. So this mbr disk, I wouldn't make it a block device or a character device, because it isn't. This is just a way for us to parse the mbr headers and the mbr stuff. But what I will create is a way to generate block devices for the partition. So get partition and then a number. I think this looks great. Block device. We will also want to get the partition count, so void size t get partition count. And then a way to get the partition. Now to initialize this MBR disk, we are going to use another block device. And then Boolean probe, and I don't know, probe or detect, to make sure that this is an actual MBR disk and not something else. All right, I think this should do it. Let's take a look at this implementation that I have here. So what I did here was that, and we talked about this when I implemented the FAT32 stuff. to basically when we are being loaded by the MBR. So the MBR, it basically has two components. It has the MBR boot code, which is basically a tiny little bootloader that just loads our own bootloader, which is stored on the active or boot partition, and then it will execute it. And that MBR code will pass us some information. It will pass us a little pointer to a tiny block of data that contains information about the partition that we were loaded from. And this is basically what I'm doing here in this detect function. I'm trying to figure out, okay, do I have this, do we have a partition or not? Were we loaded by an MBR or not? That's kind of what I'm trying to detect here. Okay, and this isn't very smart. This detection is not super smart. It just looks if the device ID is smaller than 80, because usually if the device ID is 0, then that means you're loaded from the first floppy drive. If it is 1, then it's the second floppy drive. And 80 is usually used for hard drives. But yeah, this is not the smartest way to detect whether a disk has partitions or not. Okay, we have to... There are other ways of detecting it. Basically, the way you would do something like this is... so let's go to OS Dev, MBR. Yeah, so the first part that I talked about was that bootstrap code, which does what I mentioned. And then there's also at the end of the, right at the end of the disk, at the end of the first sector, there's a little structure which contains information about 4 partitions. Now, the way you can detect whether the disk has MBR or not is to basically validate that these are valid. So, for example, you look at the drive attributes, check if these make sense, look at these LBA or CHS numbers, see if they make sense, and that's kind of how this detection usually works. It's a heuristical detection. It's not something 100% true, but if those numbers do make sense, then yeah, okay, so you'll most likely have an MBR partition. Now, I'm not going to implement this right now because this would take me a lot of time, and right now our focus is on the refactor, so let's do that instead. I'm not even going to implement this probe. Not right now. And I'm just gonna move this code into main and okay, so in this MBR detection code, I'm not even detecting anything. I'm just using that partition data from that the MBR passed us, which I suppose is fine. Okay, in that case, we don't need this right now. So I'm just gonna delete it. And what we actually need is a way to create a block device that wraps another block device, but it has a limited range. So instead of having like the full size of that block device, you can only, it has an offset. So it starts from a certain point and it has an end. And I think that's the easiest way of implementing this device. So let's create a I don't know, what would be a good name for this device? It's block subdevice. No. Range block device. I think this is fine. Okay, and all the stuff. So pragma once and include block device. This also implements a block device, but it will also wrap another block device. Okay, public. And we need to implement these functions as well as the ones from character device, which are these. All right, and these will be override. And then for the constructor, we will have a block device that we are wrapping. Begin and then an end. Or size. Range begin and range size. And private, we will need basically these three parameters. Something I haven't added in this block device is a function for returning the position. So let's add it as well. I think that's a good idea. That will help a lot. All size t, position, override. And we will have to implement that in all the devices that we created so far. Okay. And now the implementation. Range block device.cpp. Remove virtual and let's start implementing. And yes, we are adding, initializing all the arguments, range begin, and range size. Okay, now for reading, what we have to do is basically just okay, so when we initialize the device, the first step would be to seek. So we need to seek from the position, from the beginning at range begin. Why is seek inaccessible? What? I forgot to make these public. Oh no. How can I forget something like that? Weird. Anyway. Okay. Then for reading, we just need to pass the command to read. But we have to limit how much data is being read. So if device position is greater or equal to okay, so if the position of on the device is greater or plus the size is greater or equal to range begin, okay, I'm thinking of this wrong. Okay, so if position, okay, if our current position is plus size is okay, I think min or max should just solve it. So size equals minimum between the size and the how much is left in the file. So size minus position. That's basically it. And then we will just read that size and return. And we need to include core cpp algorithm.cpp. All right. For writing, it's gonna be basically the same. Although for writing, yeah, writing is a bit tricky because if a file is like a block device, in a file you can basically in the write function you basically increase the size of the file. So this doesn't make much sense. I might just return 0 because the write operation for this range block device doesn't make much sense. Although there are situations in which it might. Okay. I'm just gonna behave in the same way. So I'm gonna consider the size to be fixed and I'm just gonna write up till that size. So write data and size. For seeking, we are gonna, depending on the position, so if the position is the beginning, we basically want to seek in the device from the beginning, but we are not gonna seek at 0. We're gonna seek at range begin plus rel. Okay, for current, then we just need to call for current, we just pass the call to the device, and for seeking to the end, we are going to seek using our own end that we have. So basically, we are going to seek to range begin plus range size. Okay, size is just range size. And position is the device position minus the range begin. All right, let's see what devices we need to add this function to. Okay, BIOS disk. We don't have a position in BIOS disk. And we just need to return position here. So not something complicated. Okay, great. So now in order to add support for this MBR stuff, all we have to do is just create one of these range devices. So let's go into okay, so what else do we have here? So we have this MBR entry, which contains all the attributes from the structure. And then we just have this function which does the detection. Okay. So let's go to main.cpp. And I'm going to create mbr.h here in dev or hpp, whatever, it doesn't matter. Once, and I'm going to put this mbr entry here. Okay, and now let's include dev mbr.hpp. And I'm going to create a function here, block device. In fact, let's just do this right here. Handle partitioned disks. So if the boot drive is smaller than 80, and the device that we are looking at is okay, so let's just call this kernel partition. So if the boot drive is smaller than 80, then partition will be equal to the address of disk, because we basically don't have any partitions and we just want to use the whole disk. But if the boot drive is greater than 80, greater or equal, then we have a partition and we want to okay, there's another conversion that we need to add here. Segment and offset to linear. template type name t to linear between 32 segment and offset. Okay, this is pretty simple. So we have a segment and we have basically the segment and offset. So we just do the opposite of what we did here. We basically have the lower part is the offset and the upper part is the segment. And then we add the segment multiplied by 16 to the offset. And that's basically the whole conversion. Okay, I was editing in the wrong place. So to linear, and we need to include real mode dot hpp. Real memory, okay, memory dot hpp. And we can just change this to uint32 so we don't get a warning. And we want to linear and cast it to mbr entry. So we just call the template like this. Okay, I have a conflict, so I'm just gonna call this part. Okay, so if okay, so if the disk is partitioned, then we will initialize okay, this is a bit tricky because I want to create a range device here. So range block device.hpp. Basically what I want to do is this. So I want to create this range block device partition range or whatever. It has the device disk. The begin is the entry LBA start, and the size is entry size. And then I want part to be the address of part range. But the issue here is that this is inside the else scope. And if I do this, then bad things are gonna happen. Okay. So the best way to fix this would be to just create an initialize function. That would be the easiest. And in that case, we'll just initialize everything with 0. And I think this should be okay. It's not gonna be fine because we need to make sure. So if device is null, then return 0. And same for write, and same for seek. And then size and position should be fine. All right. So now in order to initialize this device, we can just put it like this, and then part range dot initialize. And now it should be fine because this is not going to go out of scope and it will not be destroyed. Okay, and now we have the partition, which is great. So we are done with this. The next thing we did was we initialized the file allocation table. And then we read the elf file. Okay, so there are a couple of more things that we need to implement. And yeah, I'm thinking about calling this a day because it's kind of late for me and there's still a bit of work left to do. What I'm going to do is I'm going to create a branch because I don't want to... okay. Let's show the changes as a tree. So I'm going to add all the changes in stage 2. But I'm not going to add the stage 2 old because there's no point. All the changes in libcore and also the change here. Okay, so work in progress, change stage 2 in C++, commit. And oh, I forgot to create a new branch. Okay, I'll handle this offline. Thank you very much for joining my live stream. Maybe this wasn't as interesting as the other live streams. It was a lot of coding, a lot of yeah. Refactoring is not always fun, and I get that. I understand that, and I understand that perfectly, believe me. Refactoring is part of programming, I get. That's the issue. That's the thing. Refactoring is something we always have to do. Yeah, after finishing all of this refactoring that we're doing right now, I think we're gonna be in a much better place. We're gonna have a couple of things that we will be able to reuse in our kernel, like the fat driver, and also all this infrastructure about devices, device types, all the assert stuff, the debug stuff, everything is shared. And I think this is great. And I think we're making a lot of progress here. And yeah, making operating systems is fun. If you have any questions, please let me know. I am gonna call this a day because it's already almost 2:30 a.m. for me. It's late and I like to get some sleep. Maybe I'll continue tomorrow. I don't know. I don't know for sure. But yeah, that's it for today. thank you a lot for watching, and see you next time. Okay, not much in the chat. I was looking here to see if there are any questions. I don't really see anything that I haven't answered. Yeah, thank you. Thank you guys. Looks like not a lot of people are on the stream right now, but in any case, thank you very much for joining me. See ya, and see you the next time. Have fun, and bye.